Okay, let's take a look at completing the square. So what is completing the square? Well, it's a thing that we do sometimes to, well, just change the appearance of the quadratic, but it's also for a purpose. So one of the reasons we can do it is because it actually finds the turning point of the graph of a quadratic for us. You can see a couple of examples I've written out already. It's not easy to just pick out the turning point from this standard form. Once we complete the square, writing the quadratic in a different form, it is easy to just read off the turning point. Another reason, amongst probably many others, is that we can use it to solve quadratic equations as well. So what I'm going to do in this video is show you two examples, the first one and the second one. And the main difference is because in the first one I've got a equal to 1. So the coefficient of the x squared term is just 1. It's a little bit simpler. Whereas in the second one we've got a equal to 3. Makes it slightly more complicated, but not too much. So we'll take a look at both of those. All right, so let's start it off with that first one, y equal to x squared plus 10x plus 28. Now the idea of completing the square, the name of it will become a bit more obvious why we call it that later on. But what we're going to try to do is factorize a square, even though there isn't one there. But that just means there's going to be something left over at the end. So the way that we do this is we take a look at the b coefficient, which in this case is positive 10. Now what we're going to do is a bit weird. I'm going to rewrite this quadratic. I'll leave the x squared term the same and the 10x term the same, but then I'm going to add something to it. And the thing I'm going to add is half of the coefficient of x. So that's going to be 10 over 2 squared plus 28. And leave that alone. Now you're probably thinking, hang on a minute, that's not the same thing. And you're quite right. So for me to be able to add this thing on and keep this as the same quadratic as the one we started with, I have to take it away as well. So I'm going to go minus 10 on 2 all squared. Now the next thing you probably should think is, well, what did you do that for? If I've added something and then just taken away exactly the same thing, what was the point? Well, the point is that we are trying to change the appearance of the quadratic. Okay, we don't want to change what the quadratic is. This is exactly the same quadratic as the first version there. It just looks different. All right, now normally if you were simplifying, you'd just cancel those off and then you'd be back to the same starting point. We're not going to do that. What we're going to do is sort of take this quadratic in two pieces. So I'm going to look at x squared plus 10x plus, well, 10 on 2 is 5, squared is 25. That's my first piece. And my second piece is 28 minus, again, that's 25. All right, now what we've got here is a nice looking quadratic. And if you think about how you factor quadratics, what you'll often do is think about what are the numbers which multiply together to give me 25 and add up to give me 10. Well, those numbers are just 5. 5 times 5 is 25, 5 plus 5 is 10. So we can factor that up as x plus 5 times x plus 5, or the square of x plus 5. Over here, easy simplification there, 28 minus 25 is 3. Okay, and this is what we call the completed square form of this quadratic. Now, maybe if you've already been doing some graphing of quadratics, you might recognize this as the turning point form, where values here tell us about the turning point of the graph. Turning point, which would be minus 5 and 3. Okay, so easily read off the completed square version of the quadratic, whereas it's not easy to see them up here. So we've got our completed the square form. Now, that's the end of the problem if you're just completing the square. If you're thinking about how this works in general, you might want to wonder why I added that specific value back there and took it away. Okay, now the reason why we picked the specific value of half the coefficient squared is because that's the only way that we can make sure that we always have a perfect square factorization. Okay, if this number here is equal to the square of half of this term, or this coefficient, then we'll always be able to just rewrite as x plus that number in brackets, all squared. Okay, in fact, when you get really used to this, you'll probably skip that step in the middle there, or maybe even two of them. All right, so let's take a look now at the slightly more complicated one, where the coefficient of a is not equal to 1, of x squared, sorry, is not equal to 1. So we've got y equals 3x squared, and we're going to go minus 24x plus 58. That's our second example. Now, it's a pretty similar kind of process, except what I want to do first of all is factor out that 3. So that's going to turn it into a very similar problem to the one we did first. So I'm going to factor out the 3, and I'm left with x squared. 3 out of there is going to leave me with minus 8x. Now, whether you do it with the final term or not is, it's kind of a choice you'll make yourself. I tend to, I factor it out if it's a perfect factor, but in this case, I'm going to be left with 58 on 3 because 3 doesn't go evenly into 58. So I'm actually going to close the bracket off and leave that 58 at the end. Either way you go, there are little complications that'll come in with this. So you'll see what I mean in a moment. All right, what next? All right, I'm going to try to complete the square inside here. So I've got x squared minus 8x left alone. Then I do the whole add half the coefficient of x and square it. So in this case, that's going to be plus coefficient of x is minus 8 on 2, all squared. And then outside the brackets, here we've got to be careful. We've got 58. Then I want to take away this chunk. But remember that chunk is also multiplied by a 3. So to go minus 3 lots of minus 8 on 2, all squared. Okay, so that's that little complication I was talking about. Since I haven't factored the 3 out of this, I then need to be careful about the multiplying by 3 thing when I subtract the value away again. But that's okay. All right, so next stage, we've got y is equal to 3 outside of. This we're going to be able to factor as a perfect square, but I won't do it in one step. I'll take you through it. 8x plus minus 8 on 2 is minus 4. Minus 4 squared is 16. So I'm going to have plus 16. Then I've got 58 minus, let's do that again, minus 8 on 2 is minus 4. Square it is 16. Times 3 is 48. Our second little piece there. All right. Now, the reason why we added and subtracted that particular value is so that we can factor this up as a perfect square. So we're going to have 3 outside of, it'll be x minus 4 all squared, because minus 4 is the number which squares to give 16 and adds together to give minus 8. So usual sort of factorization of a quadratic. And then down the end there, we've got 58 minus 48 is 10. Okay, so there we've got our completed the square version of this quadratic up here, which had a coefficient of x squared not equal to 1. Okay, so that's a couple of examples of completing the square. Like I said, you can use that to find turning points of graphs, or simply to rewrite a quadratic in a different form if you're required to, or to even to solve the quadratic equation. So you can use this one to find the x-intercepts as well. It's a bit different from using the quadratic formula, but if you're finding the x-intercepts, remember that you'd set y equal to 0, then you'd be able to rearrange that equation and take a square root, and you'd end up with your possibly 2 or 1 or 0 values for the x-intercepts. Okay, so that's it for completing the square.